Good morning, everyone. This is the third episode of Quant Club. Happy to talk to you. I think I'll wait a minute or two just for a couple more people to join. I just posted the link on Rocket Chat for people to join. We're getting started here a little bit early. But let's start just by answering some questions. So Liz asks, they took a long break and from the tournament are jumping back in. They're like tree models and novel artistic approaches and more focused on signals as I redevelop. Any advice? It's a good question. Any advice? Yeah, it's nothing new, I would say. There's a lot of features now. There's a lot more features coming. Getting good at feature selection and finding good combinations and sort of feature engineering are going to be super important. Just being able to evaluate like your models, getting good at cross validation and that kind of thing is always super important. And just being patient as always. It takes a really long time to evaluate models, and so just giving your models the time they need to sort of prove out or not prove out. And people have a lot of modeling slots now, so you can try lots of approaches and sort of let them run. And so you can get better feedback over a longer period of time to see how they're doing. But yeah, sort of everything is that was true before is basically still true. Liz, I think you're here. Do you have any other questions you want to ask in person?
No, not really. That's about it. Thank you.
Sure. And then the other question is, can you explain in as much detail as allowed the neutralization process the meta model undergo for the main tournament? So yeah, that's an interesting question. So the signals we get from all of you guys are normalized before we do like a weighted average by stake. And then that sort of weighted average signal is passed to the optimizer. We're not doing sort of a neutralization per se on that signal. The portfolio construction process that happens in the optimizer has constraints or penalties that basically make the portfolio that is constructed from that signal have lower exposure to lots of things. And you kind of have to do that because even if the signal is, say, neutral to country or whatever, the portfolio you construct from it might not be. And so you have to actually do it at the portfolio level. So it's basically just a convex optimization that is trying to make a portfolio that looks like the original signal as closely as possible, but has low exposure to a bunch of things. And Correlator is asking in chat, is there some development on more metrics like top-bottom, Corr, and their targets on live being available via API to set etc. There is more development on metrics. We're actually going to be pretty soon. We're going to be releasing new targets, and eventually we're going to switch over to scoring on the new targets. That will be supported in the API, obviously. And the correlation scoring is going to work a little bit differently. We're going to move sort of away from like a ranked correlation and more just something towards like a Pearson correlation, where your signal is first Gaussianized. That helps emphasize the tails a little bit, and it gets rid of some of the issues where the ranked, like this, even like a perfect score or a perfect prediction, basically if you pass the targets and do the scoring with itself, with the current metric, it's impossible to get one, like a score of 1. It doesn't really matter in the range of scores that scores typically are, but it's a kind of an annoying little property. But the new metric should be better on that. But yeah, getting more things, more metrics for figuring out TC. That is in the plans. We're also working on potentially like a newer version of TC, and that's, I mean, not super soon, but more metrics for that would come along at the same time as that. That's sort of, but that hasn't been on our OKRs, putting more metrics. But there have been some metrics, I believe, added to at least like diagnostics and whatnot. But yeah, I think a lot of the metrics are somewhat probably easier to calculate yourself now that you have access to the meta model scores. But yeah, there are some that, and some of the ones that were first made in that blog post probably make more sense with respect to the actual meta model scores you have now. Then we were using a proxy, basically the using like example predictions as a proxy for the meta model scores, but you actually have the meta model scores now, and so you can do like the feature exposure of the meta model and look at your correlation, similarity, or dissimilarity to that. But yeah. Summarize the change of dailies. So yes, we are currently we trade once a week, and we're planning to move to trading more frequently, even up to daily. And in order to trade daily, we need fresh signals from you guys. And a big reason to trade daily is that it enables more capacity for the fund. We're able to basically manage a larger amount of money if we can trade more frequently. And so just for and we are getting to a point where that will be sort of more necessary in the fairly near future. So yeah, daily tournaments kind of have to happen in order for us to trade daily. Is there any update on the current max capacity, predicted max capacity in the future? Yeah, I mean, adding the capacity is kind of an interesting question, because like in our tests, performance as sort of expected decreases as you increase AUM, but it's a fairly gradual and pretty graceful decrease. And so it's hard to say like what is the exact, it's not like something completely breaks at a certain level of AUM. And then moving to daily trading fixes a lot of that and decays much even slower. Yeah, I mean, our current max capacity, I mean, we're hoping to get to $1 billion of AUM. I think we've said that by the end of the year. And our capacity, we estimate to be more than that still. But yeah, we don't want to, we also want to allow some room to grow just through performance. So yeah, but these are kind of works in progress. And as we do, as the meta model improves, as we do more internal development on things, capacity improves. So it's kind of a bit of a moving target. Cool. Well, I am going to move into the part of the talk where I'm just going to talk about some things that I think are interesting with regard to tree-based models. First, I'm just going to highlight a couple settings from light gradient boosting that I think are kind of interesting, and I haven't seen people discuss that much. And I think it would be interesting for people to kind of explore. Basically, just ways of enforcing certain priors on the types of models built by them. And then I'm going to, I have prepared like a notebook with some interesting things you can do with trees to basically turn them into like feature creators, and basically show you how to sort of use them. And I think it's actually going to end up being a two-part thing where I'm going to go over sort of the initial construction and then ideas and show you some things you can do with it. And then next week, I will show you some even more interesting and kind of crazier things you can do with that. So first, let me just show you some interesting settings, I think, from light gradient boosting. Some of them have similar settings in XGBoost, but not all of them. Oops, so let me share my screen. So this setting right here, this monotone constraints, so this XGBoost has a similar sort of thing, but basically you can just pass to light gradient boosting or XGBoost basically a list of like 1, -1, or 0 that basically just tells the model that for that feature, so this list has to be the length of your number of features, that the output should be monotonically related to that feature. So if you do feature analysis and whatnot, and you find a feature that seems to have a pretty high, like positive correlation to the target, you might want to put a constraint on that feature to say, basically, this feature should always be sort of monotonically positively related to the thing, even as it's combined and interacts with other features. You might want to sort of enforce this monotone constraint. And you can do it obviously for decreasing, and 0 means no constraint. So you can maybe basically pass mostly zeros, and then maybe there's a few features you think should always be monotonically related. Things maybe have very strong like correlations with the feature, or like if you come up with composite features, maybe you want those to be monotonically. And it looks like light gradient boosting is sort of 3 different versions of this way to do this. They have a link to a paper that's the same for these intermediate and advanced. This is actually new. I hadn't actually seen that they have these more advanced things that supposedly behave sort of similarly, but work a little bit better. But I played with these in the past. They don't necessarily help in just like raw prediction performance, but they could help with regularization and help with Sharp and help with TC, just making your models more different. But yeah, and especially for lots of other types of problems where the relationship between variables might even be more clear, I think the monotone constraints can be really helpful. And the other thing that I think is another interesting setting is the linear tree. So trees basically work by partitioning your space, and then at the end, at the leaf of a tree, you basically have the average value that is in this little region of parameter space. And that's just basically just like a piecewise constant model. This linear tree option is to basically fit a linear model at the leaf. So instead of just a constant value, you actually have a linear function of all the that uses all the variables that have been used in all the splits to that point. That can just make your models a little bit more like continuous over time, so you don't get these kind of like step function things. It's just kind of a powerful idea to just give your model more flexibility. And now I haven't actually tried this with the Numerai data, but it's something that looks pretty interesting. And there's various ways you can regularize it. There's several other like lambda parameters and whatnot you can use to regularize these linear models. But I always, the piecewise constant aspect of trees always bothered me because I always kind of wanted my models to be more continuous. And now that's at least possible with light gradient boosting. I don't think this option exists for XGBoost, but it is kind of a cool option. Cool. Okay. So the thing to get into like what I really wanted to talk about today, I'm basically just going to be loading up. This is just code taken from the example predictions. So we're just loading up all the Numerai data using the int8 version just because it's smaller and faster to load. And then I want to talk about different ways that you can look at what trees are doing. So this is a plot that is taken from the k-bins discretizer function of sklearn. And it's just sort of demonstrating that you can break up your parameter space into discrete things and basically make a linear model on this discretized version that basically functions like a decision tree. So on the left, if you fit a decision tree to these points of data, you can see you get a model that basically goes through every point. This is a pretty high number of split decision tree, but it fits the data very well and might actually even generalize reasonably well. Whereas a linear regression fit on this data gets the sort of overall trend, but is missing a lot of the nuance. The k-bit bins discretizer is breaking up this one dimension into basically a series of regions and basically one-hot encoding those. And then if you fit a linear model on these one-hot encoded discretized regions, you can get this nonlinear function. And if you do a decision tree, you basically get the same answer. And so what this is sort of showing you is that given the correct feature space, a linear model can basically function basically just like a decision tree. And what I'm going to be sort of showing you today is that actually fitting a model like an XGBoost model, which is just a series of decision trees, can be thought of as both a discretization step and a weighting step. And so you can sort of think that all these trees are creating a discretized feature space and also giving you the weights on these features. And the kind of an advantage over something like the k-bins discretizer is the discretized features are actually combinations of all the features. You're splitting on lots of different features and ending up with so you can essentially a one-hot encoded feature that is a complex combination of a bunch of different features. And I will sort of show you how to do that and think about that. So this would just make you some fake data. And then if you fit a decision tree on that and look at how it divides up your space, you get something like this. So if you fit a decision tree with like a depth of 5, and it's a binary decision tree, you end up with basically 32 leafs, which is basically you've broken your whole parameter space into 32 little regions. And the leaf value is basically like the average of the data within that little bin. So you can see that for a region that contains like a big mixture of points that's roughly evenly balanced, the output, the leaf value for that is basically just like 0.5. It's somewhere in the middle. It doesn't have a strong preference, but a lot of these smaller bins that are more pure get a higher value one way or the other, like closer to 0 or closer to 1. And that sort of tells you a couple of things. For data that's highly mixed like this, and the Numerai data is pretty densely mixed, and it's very hard to separate, as you guys have probably noticed. Any sort of pure bin, probably like a very strong prediction, probably doesn't contain that many data points. And so you should sort of question how much you want to believe it. Because if something has a very high leaf weight, but only contains like 3 data points, it's probably not going to generalize that well because it's only based on a very small number of points. And so that's just one thing to keep in mind for what we're going to talk about in a second. And the other is like an ensemble is basically an ensemble of decision trees. You're basically fitting the decision tree and the data using some or all of the variables and then fitting another one. And you're getting sort of a whole bunch of these kind of pictures and then averaging them together. And that kind of smooths out the bin edges and gives you a better sort of approximation of how to kind of break up the space and figure out what is in each thing. But you can think of it also as just a series of features that you're learning and a series of weights on those features. And so like a binary decision tree with a depth of 5 gives you 32 one-hot encoded features. You've broken your input space into 32 things. And so from that one decision tree, you can basically get, for each input value, you'll get a 1 in one of 32 places. So it could return to, it'll always return to 32 values, but only one of them is going to be 1. Does that make sense, people? if you are thinking of it just because it's all, a decision tree is always going to output one leaf node. And if you're just looking at the leaf node, just putting a 1 for each leaf node, you're getting sort of a one-hot encoded version of your features for a single decision tree. And if you have like 100 decision trees and you just concatenate them, you would get like 3,200 things, and you're going to have 100 of them be ones. And so why would you want to do that? So this code right here is just some code for parsing for parsing a fit model. So XGBoost has this get dump function, which basically outputs a fit model as a text file. And this is just code to sort of parse that text. And basically you can turn it an XGBoost model into like a Python function. It just has actually like a bunch of if-then type statements. What we're going to be using is just the get all leaves, which also just gives you all the leaf values from the XGBoost model. So one way to think about, so we talked about how a decision tree you can sort of think of it as creating a feature and then a linear weight. And a sort of analogy you can think of is like a deep neural network, where you have a whole bunch of layers that are doing all sorts of nonlinear transformations and are being gradually trained to represent some nonlinear combination of features. And then at the very end of all deep neural networks is basically a linear layer. So you basically have a bunch of nonlinear transforms, and then you have a set of linear weights on that, and then you get the output of the deep neural network. So you can sort of think of those two parts as a feature learning part, and then just a linear weighting on these learned nonlinear features. And this perspective of taking a decision tree and making it spit out a one-hot encoding, and then having weights on those one-hot encoded things, which are just the leaf weights, has the same sort of flavor. You could think of doing transfer learning or something like that with decision trees that you've broken up in that way. So, and then you could do interesting things and sort of look at the leaf weights, which is what we're going to do now. But that's one sort of analogy of that you can make between what is going on with decision trees and deep neural networks that maybe is not obvious. So right here, we're just going to fit an XGBoost model of depth of 5. We're only going to fit 100 trees just to keep things reasonably small. I'm going to fit in target NOMI. And so this is just standard fitting of the model right here. And so after you fit it, you can, XGBoost has this apply function. And what this actually does is kind of interesting. It actually gives you the index of the node that is output for each place in the training data. So if there's, the training data has this many samples and however many features, but then if you do this apply function, you get something that is the number of samples by 100, and 100 is just the number of trees. And what this is telling you, if you look at the first sample, what this is telling you is that at this first tree is outputting node 45. The second tree is outputting node 37. And if you would look at the next one, it'd be a different set. So this is the actual numbers of nodes don't really matter, but this is just sort of showing that you can actually just get these nodes numbers, node indices, just by using the supply function. And then if you just pass this to the standard sklearn OneHotEncoder, it can basically just turn these node indices into a series of one-hot, basically just make a one-hot encoder out of those. And so if you just pass that to your now fit one-hot encoder, you can now basically just you've turned your data into just a series of into a one-hot encoded thing. So you now have something that is number of samples by number of trees times how many leaves are in each tree. So at a depth of 5, there's 32 leaves. So you have 3200, and you can see that this goes up to 3200. And you basically, for each sample, you have a series of 100 ones. So this is what the this one-hot encoding looks like of this first sample. So this is just a feature transformation. You went from your original set of features to this set of one-hot encoded features. So this is some nonlinear version of all the features. And the weights on basically, if you were to multiply this one-hot encoded version by the weights on each of these leaves, so you'd have if you take the leaves and you have the 3200 leaf weights, and you just multiply this by this one-hot encoding, you'd actually get the prediction of the XGBoost model for the sample. And I will prove to you in a second that is actually identical to doing that. And so right here, we're just applying the model and getting the one-hot encoded version of the validation, because we're going to use that in a second to sort of prove that this all works. This get all leaves function is from this tree parsing function up here. And all that is doing is just giving you all the leaf values from 0 through 3200. So you're getting 3200 leaf values. And if you just plot them, you get something like this. And so what does this mean? So this is just sort of showing you what is the average value in this little region of parameter space for each of these trees. So you have each tree has 32 leaves, and this is just sort of showing you what is the leaf value for each of those. And as I said, different ways of breaking down the parameter space give you different leaf values, and you can see there's a big variety. And some of the leaves have very strong values, and so these very high magnitude values mean that that region of parameter space is relatively pure. There's a big imbalance in that little region of parameter space, meaning that that could be a very useful region of parameter space for predicting, or it could just be noise. But hopefully the model has done a pretty good job, and that is something that's meaningful. But this is a lot of you can see a lot of the values are very close to 0. They're very small magnitude, and that's not necessarily surprising, just given that how densely mixed things are and how hard to separate things are. And so any sort of average little region of parameter space is probably has all possible target values in it, and so its average is pretty close to 0. This is assuming you've centered the target values at 0. And so these are all the leaf values. And so if you just take these leaf values and multiply them by the one-hot encoded version for a sample, you actually get the output of the XGBoost model. And that's essentially what I'm going to be doing here. So this is now the one-hot encoded version, and this is the leaves, and we're just going to dot that. And we're just breaking this down into little chunks to not overwhelm memory, but essentially we're just dotting the one-hot encoded version with the leaves, and just that is now the prediction variable. And this is just the standard XGBoost model prediction function, and this is just comparing the output of that standard prediction function to this sort of way of doing it. We're multiplying leaves by one-hot encoding, and you can see they give you the exact same answer. So this way of decomposing the problem works just fine, and you can actually do that. And so now that we've basically sort of showed how you can turn XGBoost into a feature extractor, feature creator, and a linear model. These are essentially just linear regression type weights, and you can do sort of standard regularization type techniques you might want to do on linear regression weights. And so I want to pause for a second and see if anyone has any questions, see if anything's unclear. For anyone here, please just talk or send something in chat if you have any questions.
Yeah, I did have a question. Just that you said there's 64 potential leaf nodes, right, per tree?
Well, it depends. It's just 2 to the depth of the tree. So if your depth is 5, it's 32.
Just previously, like for each tree, you had like an index between seemed like between 0 and 64, right? Like roll up a little bit. Yeah, like this that right there.
Yeah,
like,
so I think these are referencing nodes in the tree.
Okay.
And I think they probably and so this is nodes in the whole tree. So I think the leaf nodes are basically between 32 and 64.
I see. Yeah, that's just the one discrepancy. I wasn't quite tying together because you'd have
So I think you can see like there's one that goes basically because it's 0 base indexing. It goes between 32
Oh,
and
I
60.
see. Yeah, there's nothing less than 32. Okay. Yeah.
So because these are the indices of the nodes of the tree.
These are the terminal. These are probably the terminal nodes, right? Where there's
exactly. They're the leaf. The leaf nodes are the terminal nodes.
Okay. Thanks.
Yeah. So it does. I mean, because all we really care is that they're sort of unique indices that we can turn into OneHotEncoding. Okay, that makes sense. So a powerful regularization technique from just sort of standard linear regression is shrinkage. So just like shrinkage is really just sort of pulling your regression weights towards 0, and you can pull them in to sort of all the same amount, which is like an L1 type of regularization. You can pull them in based on how big they are, which is sort of like an L2 regularization. And so we're just going to sort of simulate like an L1 type thing. And so if we basically just take the sign of all the leaves, it's just saying if they're positive or negative, multiply that by a small amount and just subtract that from them. And then this is just anything that crosses 0, we're just setting to 0. So we're basically just subtracting off a little bit, the same amount from every weight, just pulling it towards 0 by the same amount. And anything that was already close to 0 and is basically pulled past the 0 point just gets zeroed out. So this is fairly, so this orange ones here are basically these shrunk or weights and versus the blue ones, which are the original. So this is kind of just doing like an L1 type regularization on these leaf weights. And that is removing a lot of these very small magnitude ones. And you might think that you could think that might be a good thing to do, because the ones that are where the leaf values are very small, you might think that's probably just due to random chance. There's not really maybe signal in them. It just maybe there's a small imbalance, and maybe that won't generalize, and maybe you just want to shrink those towards 0. And so with you now have these shrunken weights, and you can just basically dot those shrunken weights with the OneHotEncoded validation data that we created up above. And this is just multiplying by 0.5 because the XGBoost basically subtracts off 0.5 from your thing to center everything at 0. So you're just adding that back to get the same sort of range of the targets. And this is just, and we're doing this for both the original model and now we have the shrunken weights. This is just doing a scatter plot of the output from the shrunken weights versus the original. And obviously, since we shrunk the weights, they're no longer identical. But you can see they're still pretty highly correlated. And so you might want to see how well do these shrunken weights do? Have we actually improved things by shrinking the weights towards 0? And this fast score by date function is just basically taking the correlation within each era. So we get a series of correlations for each era for the validation set. And so if you look at like the sharp of the correlations, it looks like the shrunken weights actually have a much a noticeably higher sharp than the weights just fit by the standard XGBoost, which looks quite promising. Look, a little disappointing is the mean is quite a bit lower. So we've increased the Sharpe, but we've brought our actual average performance down quite a bit. And you can see in order for that to be true, you can see that the variance has actually shrunk quite a bit relative to this. And you can see like the minimum, the sort of worst performance in the validation set is improved with these shrunken weights, but relative to just the standard fitting. So we made a bit more of a conservative model, which is sort of what regularization is supposed to do, which depending on your objectives may be a good idea. But it is a little disappointing how much the mean drops. So another thing we could sort of try to leverage using the same idea is what I was talking about before. How many data points are in each of these little buckets? And you can do that kind of easily since things are OneHotEncoded. You can basically just count in your training data by just summing along this axis how many points are there in the training data that are basically how many for the decision tree, how many times basically how many data points are in this little region of parameter space defined by a given decision tree. So like just like I was saying with the decision trees, this plot up here, we're basically just counting the number of points in one of these little bins. And so a bin that has a very small number of data points, maybe you don't want to believe it as much as something that has more. And so maybe we want to shrink things that have a small number of data points more than we want to shrink things that have a larger number of data points. Because we're sort of less confident about a large prediction from a small number of data points. And so yeah, so you can start that first by counting the number of data points in each of those regions of parameter space. And you can see that there's a pretty wide difference. You see some have like 5,000 data points, some have like 90,000 data points. This is right here, just taking the square root of that number, and we can make a shrinkage thing by basically just 1 over the square root of n. So some things will get shrunk a lot. So things that have a very small number of data points, and some things will get shrunk just a little bit, but with this 1 over square root of n rule. You could potentially use other rules. This is just sort of a reasonable heuristic. 1 over square root, lots of things sort of vary by 1 over square root of n. And so yeah, this is just a reasonable shrinkage rule I came up with, but other things are of course possible. But yeah, so this is just sort of say we're going to shrink things that be less confident about things that have a very small number of data points in that bin, and shrink things less that we're more confident about. So just like we did before, we're going to just use the sign of the leaves, but now we're going to multiply it by the shrinkage factor. So we're shrinking things differentially, and just by some constant. And then again, when things cross 0, we just zero them out. So this is what things look like after shrinking this way. And you can see things look quite a bit different. Things are not shrunken evenly. And some of these very high things are brought down quite a bit, probably because they contained much fewer data points, which is sort of to be expected. And then you can again take the prediction from the shrunken weights. And if you just look at them versus the original thing, it's kind of interesting. Actually, the weights shrunk in this way are actually more highly correlated to the original predictions than just doing the sort of more simple type of shrinkage. Yeah, I found that kind of an interesting fact that the predictions change less when doing this sort of scaling by 1 over square root of n than just shrinking everything the same. And then you can look at performance. Again, look at using this function to get the correlation within each era, and then again, we see that our sharp is a bit higher than it was before when shrunk in this way. And our mean is a little bit less than just the standard way of fitting, but it's not a huge decrease. So we've increased our sharp, but we haven't completely killed our mean by shrinking in this way. You can see that the variance is a bit lower too, and the worst case scenario is a bit lower. So this sort of original sort of simple shrinking seemed to have a little bit increase, a bigger increase in sharp because it has a bigger reduction in variance, and had an actually better worst case scenario. But this other version is better at maintaining the sort of mean performance. It's possible you could do something intermediate and even get better values. I didn't tune any of these things super well. This is more just to kind of put these ideas out there for people to see different ways of thinking about trees, and regularizing the outputs you get of them. Basically, just trying to be more aggressive in how you regularize than just XGBoost might by itself, and just sort of showing that even with a small number of trees, you can see some like reasonable improvements in sharp just by doing this sort of simple post hoc regularization. Let's see. So yeah. So now that you have this sort of representation, you can do lots of interesting things. And I don't think we're gonna have time to talk about it this time, but next week I want to talk about how you can sort of use this tree representation and sort of fit things per era and look at how the weights change across time and try to get some insights for how you might try to predict into the future, looking at how the weights evolve over time. And because now if you fit like linear regression weights per era on this OneHotEncoded feature version, these linear weights are sort of representing a nonlinear transform from features to target, and sort of looking at how that evolves over time might be an interesting way to look at the data and to try to predict where things are going. So that's what we're going to talk about next week. And I'll just show you some of the cool plots and stuff. This is like embeddings of things of how these weights change over time. But yeah, we'll get into that a bit next week. I just wanted to stop here. I think we have like about 5 or so minutes left, just for any questions to discuss any of the things we've talked about in this so far. Liz, you look in thought.
I'm just thinking of the, I'm skilling back up, so I'm processing.
Yeah, there are a couple of questions in the chat there.
Oh, like maybe I have to stop sharing to see that. Oh, yeah, I do. Okay. Let's see. Let's try to answer some questions. Andres, could fitting distribution of samples within each of the leaves, especially when there's higher rate, be used for estimating uncertainty prediction? Yeah, that seems totally possible. The idea here, Liz said there's a couple of 31s. Yeah, that's, I think, just because of the zero-based indexing. The idea is to avoid overfitting into subspaces with very few data points. We get similar performance by setting the number of instances in each leaf instead of regularizing the linear regression at the end. Yeah, that's a reasonable parameter to try as well. That's yeah, I mean, generally, especially it sort of depends on how deep your trees are. Usually that's, unless you're going to very, very deep trees, that's pretty for like the data set with 2 million data points in only like 32 leaves, you're generally going to have a lot more than the sort of standard minimum is, but you could potentially set it to something pretty high just to make sure you're not getting any super yeah, I mean, that's a potential way of doing it too. Someone is asking, why not just use L1? Yeah, I think there are some leaf regularization things that can be applied, that some parameters that you can use during fitting. And yeah, I mean, I haven't played with them that much. They might work as well. This is part of this was just sort of showing that you can sort of turn this into a linear regression, and then use sort of linear regression like techniques, and potentially do something more custom than just using something like L1. Just sort of showing that now that you have this in this linear regression space, you can have a lot of options for regularizing. I was just using L1 as an example, and some things like that are kind of built into like XGBoost. But yeah, you have a lot more freedom when you can sort of do it yourself, when you actually have access to the weights. Yeah, if you want to decrease the magnitude, let's see, if you want to decrease the magnitude of leaves with few samples more than L2 would, the traditional mean would be applying L1. L1 is used part of the split criterion. Yeah, yes, this is all true. Yeah, the point was not necessarily to say you should do L1 or L2, and because these things are built in. The point is, you have more flexibility in how you do things. Like you can use this like 1/square root of n rule. You can sort of combine things. You can set sort of your own thresholds post hoc. There's just, you have a lot more sort of options in how you want to handle things when you have actually access to the weights. And this is just sort of, meant as an example of one thing you might want to do when you have access to the weights, not necessarily like the best way to regularize these things. That'll maybe make a little bit more sense next time when we actually show more things you can do from this sort of OneHotEncoder feature representation. Does that make sense, Jacoby? And yeah, Jacoby, if you, I would be curious, have you had much experience or luck using the L1 and L2 things in XGBoost that are the things that are built in? Because it's using a custom tree algorithm with L2. That's interesting. Yeah. Yeah. So I mean, as I said, by doing your own sort of custom regularization afterwards, you can use things like basically like L1 scaled by number of leaves in the node in the leaf nodes, about number of data points, like this 1/square root of n. Yeah, it's just sort of a way of making more custom. He's shrinking not towards 0, but towards the parent leaf value, or sort of parent node value, which actually, it makes a fair bit of sense. You're sort of, basically sort of the parent is going to be less pure and probably a smaller, like probably closer to 0. And so it's maybe a better value than 0 to shrink towards. That's interesting. Yeah, this is, part of this is just I wanted to highlight, as I said, a sort of commonality in ways you can think about like a deep neural network and transfer learning using the last linear weights and an ensemble of trees, which you can turn into a feature encoding and a series of linear weights. Just because that, yeah, basically you can sort of think of everything as linear regression in the end. All of the all of our most complicated and best performing machine learning techniques, you can sort of always turn them into like a linear regression problem. You can just think of them as just different ways of creating features and then performing linear regression. And that sort of perspective is nice just because there's so many ways to regularize linear regression that are pretty well studied and well understood. And it's, yeah, I mean, it's a very powerful framework of thinking about things. Someone is, I have not seen this, a Facebook paper which did something like this using XGB as a feature generator and then throwing a linear layer on top. That's interesting. I will open this and check this out later. Yeah, so one thing I should also mention is light gradient boosting has a method that is like refit, I believe. And basically refit is basically just finding new leaf values for a already fit decision tree structure, which is basically just like fitting a linear regression on these OneHotEncoded on this representation. It's basically equivalent because light gradient boost has a way of to basically just finding new leaf values rather than just fitting the linear regression, but they're sort of equivalent. XGBoost doesn't seem to have something quite like that, and I don't have good parsing code for light gradient boosted models, but maybe some exist. I should also mention, yeah, I will release this notebook after next week with some more comments so people can have access to some of this like tree parsing code right here, because it can be useful for just sort of seeing what's going on inside the decision tree. And I also think it's kind of cool. You can turn a fit decision tree into just a Python function that you can just run anywhere. And so it's, yeah, it's basically, it's just pure Python of just a bunch of if-then type statements. And so, yeah, I will release that with probably better comments after the next one where we get into the more interesting thing. Cool. Well, I think we're pretty much out of time. Any final questions before we wrap? Cool. Well, thanks everyone who showed up today, and I will hopefully see you guys next week. And I think, yeah, I think the thing that we're going to be talking about next week should be pretty exciting. So hope to see everyone there. Okay, yeah, thanks a lot, everyone. See you next week. Bye.